Happy Wednesday. Thanks. So today, from Florida International University. Eric has a bachelor's and master's degrees in physics. He did his PhD in physics, or in curriculum instruction, from Arizona State University, where his dissertation focused on how the reorganization and restructuring of introductory physics courses should include energy as a common thread throughout the curriculum to promote more expert-like practice from undergraduates. Very exciting stuff. So his research interests right now include ideas around modeling instruction and the implementation of modeling instruction at FIU. And recently, his work has moved to address issues in the role of social engagement in student learning, which range from studies of semi-formal learning environments to an upcoming fMRI-based study of students. So without further ado, please join me in welcoming Eric to the Create for STEM seminar series.
Thank you. First of all, thank you for having me here. It's been a really fun morning, and those fall colors are super beautiful. And then also, everybody should say thank you to May. Anybody that's ever coordinated one of these knows what a pain it is. So thank you for helping and making sure that everything was well coordinated, well organized. I would like to start by acknowledging all of my collaborators, current and past. The things that I'm presenting today are in part mine, but also very much belong to the people that I work with. And so this is our physics education research group. It's a smaller set of another group. Hey, Brad. That's funny. All right, so I want to start, and I'm going to start with something that's coming next. I want to tell you about FIU and give you a little bit of background. So FIU, within the next month, will be announcing an open search for multiple tenure track or tenured faculty in science, engineering, mathematics education, discipline-based education research positions. Now, I say this in part because there might be graduate students here that should be paying attention. Maybe they would like to apply for these jobs, postdocs. I am not trying to poach faculty. That's not my goal. What I want to do is I want to tell you about the things that are happening at FIU. And so one of the keys to a university is the hiring practices. And so right now, FIU has made a pretty big commitment to hiring multiple people in discipline-based education research. And I think that this is consistent with another part of where we are and what we've been. So earlier this month, we hosted the President Obama's science advisor, John Holdren, at FIU for a visit. And this is him. Actually, John Holdren is a physicist. And when he went to this modeling instruction physics course, he was there bugging the students. And look, the students are all like paying attention and listening, and all the other people are mucking about on their cell phones. Tells you something, doesn't it? But this tells you something else about FIU and where it is. And I think, I would like to argue, some of its place in the national dialogue on STEM education and discipline-based education research. And so those are the more recent things, and I want to then go backwards in time and show you a few things that are sort of indicators that we ought to be paying attention here. So how many of you know about the Learning Assistant program? Have you heard of this? Learning Assistants developed at University of Colorado with Valerie Otero. FIU now has the largest learning assistant program in the country. We currently have over 168 learning assistants supporting 98 different courses and impacting over 6,000 students this semester. Learning assistants are sort of a teaching test drive is the way we think of it. It's people that are in the science disciplines and letting them think about what teaching might be like. And that's good for people that are going on in science, but it's also good for people that might be interested in becoming teachers. And so what you see here is we have a number of people. The program has grown rapidly, and it's grown across multiple disciplines. And one of the reasons that you might think that this has happened is, now stepping even further back in time, is that physics is where it started. And this was where my research and my research group's work has primarily been. What I've got here is a graph of the number of declared and intended physics majors, starting in the early 90s and going up till last fall. So that's, so spring 2014. All right, so the title is still okay. And one of the things that, so you look at this and you say, oh, that's interesting. But wait, isn't FIU now the 7th largest university in the country? So they ought to have a lot of physics majors. So turns out that when you normalize it to the growth in the size of the university, or the growth of the number of undergraduates, it represents about a 400% increase in the number of physics majors. Now, this is important because FIU is the #1 source for Hispanic bachelor's and master's degrees in the country. It is in the top 10 in physics degrees, and the demography, the university's president, Mark Rosenberg, likes to talk about our demography is our destiny. And so you see here that 60-ish% of the university population is Hispanic, 15% is black, which means that 75% are from statistically underrepresented student groups. And this is really important because I would like to argue that FIU can serve as sort of a laboratory for science education, investigating effective implementations of science education. And so the story that I want to tell a little bit today is how I got involved, what my role has been, and what I think FIU is doing. And so what I want to argue is that FIU is sort of working very hard on a number of fronts in this area, trying to be involved in the public dialogue, trying to be at the cutting edge of research, and trying to really build the institution through discipline-based education research. And I think that one of the roles that I played in this whole game is that when I arrived at FIU in 2007, so right about here, one of the things that was happening is we were starting to see success. And so my role in physics was to try and understand, what is this success? Where is it coming from? What can we make of it? And so I did do my graduate work with David Hestenes. David was a philosopher before he became a physics professor or a physics student, and which kind of shows in his writing. And so he thinks heavily about theory. Theory is important to him. And so I tried to look at what were some of the ways that I might think about this complex process of building up a successful both course transformation at the introductory level that translated, or maybe didn't translate, but I think translated to a growing number of students involved in physics, and ultimately, at this point, it involves across the entire university, from the president through a number of areas and a number of disciplines. And so my idea was to try and think about what is it that I can do to think about this complex phenomena. And option one would be just break it up into chunks. This is what physicists love to do, so let's do that. The problem is that the chunks are all related. And so one of the things that we saw was growth and diversity. And we think that there are some pretty complicated interactions among the things that are happening. And so I went with option 3, which is a little bit of both. Around this time, I was reading a paper by Paul Aubusson on an ecology of science education. And he was developing an extended metaphor for science education reform and using an ecosystem. He used the Great Barrier Reef as his example. And he identified he identified a number of shared characteristics among these two systems. So an ecosystem is, of course, a complex web of interconnected subsystems, and the transformation of a physics department is a complex web of different kinds of interconnected subsystems. And here were some of the things that he identified in this paper were complexity, homeostasis is keeping the same over the time, succession over time. So that's a good way to change physics departments. Fitness, generation and regeneration, opportunism, and reproductive mutuality, maturity, fragility, variational evolution, purpose, and knowledge. So he saw these things in these subsystems, and I'll defer to his paper, which I thought was sort of excellent. So I'll not talk too much about it. But one of the things that we know about ecosystems is that diversity is often a sign of health in an ecosystem. And the question that we all ought to be asking in education transformation is about sustainability and what are the things that allow an ecosystem to be sustained. And so I wanted to try and use this analogy to understand, or to apply this metaphor to see what I can gain with it. And so now I'm this educational ecologist, which doesn't mean I know anything about ecology. Don't get me wrong there. So I wanted to ask sort of what are the relevant subsystems, and how can we use research to document, identify, and characterize these subsystems? How do the subsystems interact with each other? What are the relevant background environmental features? FIU is a unique sort of place. What sorts of things there seem like they may have mattered in the development of this course transformation, or this transformation of the physics? I don't want to say the whole department, but the growth in the physics department. So the first place I will start is, I'll start with modeling instruction. Modeling instruction is a sort of three-part thing. It is based on the work of Hestenes et al. And Hestenes primarily focused at the high school level. My work is primarily focused at the university level. So trying to say what is modeling instruction in introductory physics, I think of three things. Is that, first of all, modeling is a theory of science. So that science proceeds as people are engaged in the process of building models, evaluating models, poking holes in models. So this is what science does. All right? So science itself is a modeling endeavor. And that if we think that we ought to be teaching science students authentic scientific practices, we ought to be talking about how we can build a theory of instruction that gets them to do this. So science learners ought to be engaged in the processes of modeling physical phenomena in physics classes. And then we developed actually my colleague Dwayne Dabian developed modeling discourse management, which is sort of an approach to managing discourse so that students are engaged in this modeling process. And so I'll leave that. That's sort of the idea behind modeling instruction. It has a bit of history at FIU. It started in 2002 with the Center for High Energy Physics Research and Education Outreach. Yes. It was basically a 10-year project from the National Science Foundation. Part of it was high energy physics at CERN. Part of it was implementation of modeling instruction, and how could those two work together. Interesting project, but not what I want to talk about today. It started by developing modeling workshops for high school teachers, and then we sort of realized, wait, if these students are getting good classes from high school teachers, they're going to come to FIU and they're going to get regular old drill, lecture and drill type stuff. That's not cool. Let's give them modeling classes at FIU. And so in 2005, basically started the first modeling class at FIU. Excuse me. In 2007, there was funding for PhysTech from PhysTech, Physics Teacher Education Coalition. It's peripherally involved in this modeling instruction, but one of the reasons that it was there is that A, physics teachers learn or teach like they learn. So if you give them a good introductory course, we think that matters a lot. And it reified for the department that what we were doing was real. This is money that comes from the American Physical Society. So it's sanctioned in a way that's sort of interesting. In 2011, we got a TWOS grant for transforming modeling instruction. And just this past year, we had a new classroom. Cool story is that the provost, we were scheduled to have a 500 student stadium style lecture hall built. The provost at the time went to University of Minnesota, saw a bunch of active engagement classrooms, came back and demanded that the architects stop working and say, we're not doing this. If we do this, we're making institutional commitments that can't be undone easily. You can't do active engagement in a 500 student lecture hall. So the provost must have been listening at some point. So I don't know how, but it happened. So we now have, since then that we've built this 96 student modeling instruction classroom, and you can see it sort of there. This is a discussion group, and there's another one back there, and we can put 96 people, and it's really great. They've got these really expensive, they've got these things right here. They're really expensive monitors. And the fact of the matter is they've got a whiteboard on the other side, and that's what gets used. A $7,000 whiteboard. Anyway, that different story. All right. This is sort of the idea behind modeling instruction, and I wanted to show a clip. So this is a clip from a modeling instruction class. At this point in the semester, students have been working on models for kinematics, 1- and 2-dimensional models. They can use constant acceleration models. The students are working in small groups, and they're working on a lab that introduces energy, and that sort of changes the nature of the discussion. Everything up to this point has been descriptive. This provides some causation. So the thing that they're going to be working on, they've held a motion detector up here, and then they've dropped basically a playground ball, and it goes down and it bounces. And the question that they have been asked is, why doesn't it bounce back as high? And so one of the things that we think about models and modeling instruction is that the model itself is a collection of coordinated representations. So the representation they're working on right now is energy pie charts, and we'll sort of see what that means. Here's what you're going to see. And this is primarily, well, this clip wouldn't exist without Vashti Sawtelle, who's not here, but she's now a faculty member in the Lyman Briggs College, and she was my first doc student, and she's awesome. So this wouldn't happen without her, but I'm glad she's not here because I couldn't figure out how to, she worked very hard to make sure it was transcribed and subscripted, and I don't know how to make it show up on my new computer. So here's what you're going to see. So this here is a learning assistant. She is a student that has taken the modeling physics class previously and is now coming back to facilitate discussion and interaction. This student will do the majority of the talking, and he has a bit of a heavy accent, and so I'm hopeful that you can hear and understand what he's saying. But I think you'll enjoy this. All right. So the clip is about 2 minutes long. So good? Yep. Questions? Oh.
How would you model anything? How would you model anything? He's talking on pie. I don't think it makes sense to me.
That's exactly what you're model anything. Okay.
No, forget pies. Pies don't make sense at this point.
composing the pie.
Okay, then makes sense
That's
to me
a
how
foundation of our theory right now.
Like the pizza,
the energy that we have
it's like
is the size of a 12-inch pie, right? When you drop this pie, okay, its potential energy is the 12 inches of pie, right? And this 12 inches of pie is all different types of energy.
there's nothing
So
closing in it.
at this point in time, at this point, it's 12 inches of pie, potential pie, right? And as the reason, some of this pie is changing into kinetic pie. So they're saying like it's brown pie, and blue pie, and it's brown pie, right? Potential pie, and it's falling, it's slowly changing to blue pie. When it reaches the ground, stop. It's blue. It's all blue pie. And as it hits, it loses some blue. It's reducing its blue pie.
there's blueberry everywhere.
There's blueberry everywhere because the elasticity of the ball is not complete.
And because of pipe.
Because we buy first. So we lose blueberry in sound, and we lose blueberry in heat, and we lose blueberry in all different forms of it.
And then when it comes up with the one pie that now says the
It's still blue pie coming up, but as it goes up, it goes back into brown pie. So as it travels
brown pie is kinetic pie, and then
no, brown pie is potential pie.
okay.
Wait, let's define these types of words. So what exactly does potential or brown pie mean?
Alright, blue pie,
Blue pie
it's kinetic pie.
Okay.
Kinetic energy.
Well, how would you explain it to someone that she doesn't know anything about kinetic energy?
It's the blue pie is due to motion, and it's increasing, getting faster as it goes down. So it's increasing its kinetic, so it gets more blue as it goes down.
Okay, that makes sense.
Right.
And then when it hits the ground, it's like
All blue pie. All of it.
okay. So then when it comes back up,
So as
it's
it goes
changing
back
back
up, it's
to brown
back to
pie.
brown pie.
And that's potential pie.
And that's potential.
And then
So when it reaches the highest point, it's peak.
so when
It's
it's
all brown pie.
what? You have
The highest point that it reaches at it's all brown pie.
and then when it goes back down to
And it's going back down,
it's going back
it's the
to
blue pie.
okay, that makes
And that's blue and brown
Okay,
pie.
I'm gonna need you to explain that,
Negative
Mr.
separation.
I'm not joking.
and then you have
He's one of my favorite students of all time, you might have guessed. So what they've done there is they've negotiated out how they might use this tool, this representational tool, to understand a phenomena. And so one of the things that we think is happening, and so then they would go on and they would use this in blue and brown pies, and this helps them understand why the ball doesn't bounce back up to the same height. And so one of the things that we see happening is that we see students taking some ownership of what they know and the ways in which they know it. I never would have talked about blue or brown pie. There would have been no blueberry, but those students were into it, man. They were, and I think they got it. I think I've got evidence that they got it. I don't exactly know how to say that for sure, but I think they've got it. And so this is the kind of thing that happens in a modeling class, all right? And I'm not going to go much further. I'm going to defer that till tomorrow, where I'm talking in the physics department, and invite you all there at 4 o'clock? 4 o'clock, and I don't know the room, but come. I'll do more of that tomorrow. So I'm quite confident that if you were in a class like this, you want to be involved in. This is something you want to be engaged in. These students are making meaningful connections with each other. They're laughing. They're having a good time. They're learning something, and I think they've got it in a way that sticks. So this modeling instruction component seems to me to be one of the very first foundations of an educational ecosystem. And so now what I want to do is I want to give you my model for what the educational ecosystem sort of might look like. And I would say that, you know, in this case, the educational reform played some sort of essential part. It was something that students could rally around. It provided an entryway for students. It helped build up and support a community. I'll talk a little bit more about the community later. And that it helped develop students into advocates, right? And that once students became advocates for this, then we can sort of think about these sort of three things, the reform, community, and advocacy, and how they might interact. That the students interact because by being participants in this, they become more advocates, which then allows them to induct new people into the system. And I want to argue for two things that are sort of background elements, which is, number one is that FIU is a Hispanic serving institution that I think must have some relevance in this situation. And then we've been working on this from a learning as participation sort of framework and trying to understand what we think is happening based on that. All right, so back to our educational ecosystem. So if this is what I think is happening, then my job as a researcher is to develop a program of research that addresses these sort of three areas. And I'm in some sort of mixed state on where we are with these. So the very first one is, I should start by looking at the very specific formal learning environment, the classroom. And that's got a number of sort of studies that could be done: student understanding, attitudes, looking at retention and persistence, and then thinking about the curriculum and the pedagogy. There are a variety of things that you can do there, and that, I'm not done, but I'm more done there than I am in any of the other areas, right? Going beyond the classroom, though, because it would be foolish to think that learning just happens in the classroom, and we have to think about how the community evolves from this classroom, that the next step up would be some sort of semi-formal or formal-informal learning environment, where we look at the interactions between what's happening in the classroom and in a more semi-formal or informal settings. And so in order to do this, we've undertaken a couple social network analysis of student interactions. We're trying to design up studies of transfer, which are noted to be very hard. And then from this third layer out is that you'd want to think about this ecosystem and try to think about it as how sustainable is this, and how important are those contextual features that I think are sort of backgrounded but important. And so this is the way I've been thinking about the research program. And so this is where we've been. And so starting at the classroom focus, the very cognitive kind of sorts of things that you might be looking at. Well, here's some of the evidence, all right? So we see improved conceptual understanding. That's not all that exciting. If you are involved in discipline-based education research, this doesn't surprise you. If you are not, this is exciting, but I'm presuming we're all a bit more advanced than that. All right. The second one is we looked at students' attitudes towards physics. And introductory physics classes are very good at making students' attitudes towards learning introductory physics worse after they've been through the class. We found we published the very first improved attitudes for introductory physics, and we have recently, last year, published a replication which shows that, so this one was one classroom showing positive shifts. Now we've shown it across multiple instructors and multiple sections for several instructors. So what you see here, the blue is the pre and the red is the post. So we're pretty confident that we're seeing these actual attitudinal improvements. The next place we looked was the retention in introductory physics. This is an interesting place to look because, I mean, as nice as it is to have a good attitude and as nice as it is to have a good conceptual understanding, we ought to know that they are able to go on in physics. That's a real measure of success. And so retention is an important thing to look at. The typical lecture classes are around 50-ish%, 55. And the modeling classes are at about 91%. And that these measures of student success are equitably distributed between men and women, and statistically majority in the statistical underrepresented groups that are prevalent in our classes. So those were the first sort of three obvious ones. And then we started doing something else, is that we said, all right, if this is what's helping us build up the number of students, which is eventually engaging other people from other disciplines, we ought to think about what does it mean to be interactive engagement. And so we did this network analysis study of the class. And so we asked students, who is it that you work with to learn physics? All right. So this is all 30 students in a modeling instruction class. You can see that these students all either are named by or name one other student. And many name multiple students. This is a lecture section. Now, you can see that there are a number of smaller little dyads, triads, and other clusters. And there's this line right here that is actually all the students that don't say they worked with anyone. All right? Which is not surprising. I mean, if I asked you who you talked to while I was talking, you didn't talk to anybody, you know? So it's not surprising. The other thing is, this is a class of 120 students. At the end of the semester, only 40 of them showed up to answer our questions. So, like, at first cut, that's even terrible, right? So, so anyway, this tells us that these classes are being successful in some ways at getting students to talk to each other, to engage with each other. Now, so this is, so if I wanted to try and understand this from a very cognitive thing, well, I could understand maybe the FCI gains, the conceptual understanding gains. I could maybe understand the CLAS gains going strictly cognitive. The retention, where students are passing the class at a higher rate, you might be able, that's a little tenuous, but when you look at the theories behind retention, especially with underrepresented students, you have to look at how students are engaged in the academic and social fabric of the university, or of the learning setting. And so what I felt like is, well, yeah, maybe, but there's probably something more. And for sure, persistence wouldn't be explicable by strictly cognitive means. So I want to push on and talk about the next thing, is that this interaction between the formal and the informal, and the building of a community of students. All right. So these modeling classes happen in this classroom. When the classroom's not in use, students hang out there, and they do stuff. They do stuff that includes solving physics problems and calculus homework and advising, oh, don't take Professor Brewe, he's a jerk. You know, like, they do these sorts of things. But they also do other sorts of things. They have Society of Physics students meetings. They do homework. And there are some things that you're like, well, I'm not so sure how I feel about this. Thanksgiving dinner. They host a Thanksgiving dinner in there. It's a little weird, but it seems to matter, and it's always well attended. And they have game nights and movie nights. And all of a sudden you're like, wait a second, my physics class is being used for this? Well, what I saw is that these students had taken this room and made it their own. And so because they said, look, we've got a place to hang out, let's take it and do stuff. I never would have sanctioned a game night, but they said this is something that's important and valuable to us, and so we let them run with it. And so I tried to think about ways in which we could try to measure community. And so I did this study looking at, I asked them, who is it that you work with to learn physics? And this was the first social network analysis study that I had done. And what we found is that there were a number of people who sort of didn't really talk to that many people, but there were a lot of people that were really deeply connected. And so it sort of led me to this kind of question of what kinds of things can we know about the actors, or who's in the network. And so we did a little hypothesis testing. And so we tried to look at this physics learning center community. And so this is a sociogram of the links among people in the Physics Learning Center. And this tells you about how much time they spent in they reported they spent in the Physics Learning Center each week. So what you see over here, a lot of people that spend 1 and 2 days. Over here, people that are not linked to anyone else, they also spend less time. People that are on the heavily linked side tend to spend much more time, 5, 6, 7 days a week. So time seems to matter. And in fact, we asked about gender as well. All right? Oh, no, physics major. Physics major. So people that are not physics majors, not surprisingly, are not deeply engaged in a physics learning center. People that are physics majors, right here, they tend to be. It doesn't mean that you can't be involved if you're not a physics major, but typically that's the way it works out. And so we did the hypothesis testing, some linear modeling, and what we were able to find is that engagement in this community of learners did not depend on gender. Gender did not predict how central you were. This is important in physics. Physics is typically about 20% women. Participation did not depend on having been in a modeling instruction class, which I thought was a little bit surprising. You might have hypothesized, oh, they talk together in the class and then they kind of go in. Well, it turns out that that's not the case. And the participation is dependent on time spent in the community and whether you're a physics major. And so I felt like those were pretty important findings that, hey, there are a lot of ways of thinking about the very, conceptual understanding questions, but participation is a way of really thinking about this that is more sustainable, because I'm not doing these things, right? I'm not sanctioning game night. They're doing it and carrying it out. And so if I were to try and think it more like a Vygotskian framework, you might be able to argue that we could explain some of the gains and the C-last shifts and the retention, and even probably some of the persistence, which is a different question than one that's still open. But you can absolutely talk about the community, all right? The community that was formed. And maybe even the sustainability, but that's a different question. And certainly you can't talk about the replicability. At which point you have to think about, what is the third subsystem? And I've told you that I think that it's advocacy. And advocacy is important because it makes stuff happen, all right? So we've got, as much as I would prefer it that they didn't matter, chairs, deans, provosts, and presidents are really important, as well as people from the outside. They can provide protection, they can provide support, they can dissuade people from engaging in these types of behaviors, they can position efforts to succeed within the university, and they're really a great liaison with the broader community. Towards this, here's a picture of Mark Rosenberg, the president at FIU, in November of 2012, testifying at the PCAST, participating in the PCAST process. And so the leadership matters. But it's not just the leadership, the faculty matters as well. I mean, the faculty are the ones that provide the funding, they develop the programs. We're engaged in the research, we're looking for opportunities, provide mentoring, and then importantly, promoting physics as a major or career, and promoting physics teaching as a career. But the faculty aren't enough. We have to also think about students. Students are probably the most effective advocates to other students, right? Students do, at this point, the bulk of our recruiting. We have about 4 times the number of requests for space in the modeling classes as we have available space. They provide enthusiasm that I am I'm waning on. No, that's not true. But they have a lot more of it. They provide mentoring about things that are really important. They help establish directions that we wouldn't have thought of. And really importantly, they perpetuate this culture. And so if I think about it as trying to think about these three subsystems, this allows me to think about not only the very tenuous, oh yeah, cognitive things and the sociocultural things, but really how we ought to think about this as a set of interacting, cultures or subsystems. And that is the way we will need to think in terms of thinking sustainably and in terms of trying to replicate this. And so now we get over to the part of the talk where I'm way out over my skis. All right. So if I were to try and think about cultivating an ecosystem for educational reform, first, I would say that we need to engage faculty in educational transformation. I like to use Joe Handelsman's paper on scientific teaching. It really speaks to scientists about the ways in which they approach education. In that teaching and learning research and teaching are both about learning, and that we ought to maintain the same standards of rigor and evidence in teaching as we do in research. And that we ought to be engaged in measurement, analysis, reflection, revision, and then scaffolded induction. This is what you do with graduate students. It's what we ought to be doing with faculty as they become teachers in university classrooms. That's where I would start. I think that's probably the most important part. The faculty are the longest running thing and the continuous piece at the university. Administrators come and go, students come and go, but faculty, we don't change. I'd work on developing a sense of community among the students. I think that reforming courses is one way to engage the active participation, but it also provides opportunities for collaboration, and it allows students to become integrated into the fabric of the university, which all of the theory and research has indicated is important. And then the last thing I would do is I would try and cultivate disciplinary advocates. So we've been running a discipline-based education research group, which is an informal set of discussions around science teaching. And we serve beer. Yes, it's important. Danny can tell you that this is an idea we stole from Noah Finkelstein at University of Colorado, or maybe not just Noah, but he said, look, get them over and give them beer and see what happens. And it actually works better than you'd like it to. But also to provide them with some prestige, provide them with opportunities for money, opportunities for travel, opportunities to do things that they want to do, but it's not part of their day-to-day job. And so those would be my recommendations for cultivating these ecosystems. I'm happy to talk more about it, but for now I'd just like to say thank you again.
So the floor is open for questions. Anybody have questions?
So I was interested in your analysis of the students who took advantage of the open room, the physics algorithm. I wonder, have you thought about doing sort of a matched analysis among the physics majors? Who uses it, who doesn't use it, the non-physics major, who uses it, who doesn't?
Yeah. So that, yes, in fact, we are working on it right now. I got funding from National Science Foundation to do a network analysis of student retention and persistence. So we're trying to build up both a cross-section across different grade levels, but also are they being sort of transitioned in. And in order to do that, we were having to interview students. And from first pass, I just assumed everyone was engaged in this community of physics students. And as I've been doing the interviews and looking at the data, I now know, oh, no, actually they're not all involved. And that they become involved in other ways. I will say, I think that the students that are involved tend to have these richer experiences, but that's off 7 interviews, so I'm not comfortable with that finding. Yeah.
So I'm just wondering if the fundamental concepts of the education ecosystem that you've sketched here might apply to online environments.
Yeah, that's a hard question to answer. I have a student, Seth Manthe, who is doing biology education, and his project has evolved a bit because he's a biologist. There you go. But it involves looking at differences between a blended and an online, a purely online biology project, and he found no differences in terms of conceptual understanding. He found some differences in terms of student attitudes. Student attitudes in the online courses seem to have, more positive attitudes. He found no differences in success, and surprising, the one that really surprised me is that the student networks were relatively similar. Is that he was seeing similarities in terms of how networked they were, and that's kind of stunning. Now we think that one of the problems might be that the students this is the lecture component, the lab component's still mandatory in person. And so maybe they're building up those networks based on their lab sections. But certainly the role that online universities and online classes is playing is going to be important. You could certainly say that MOOCs have been the educational transformation. Is it developing a community? Yeah, to an extent. It's just how effective are they, and what's the advocacy going to be moving forward? Because I think we saw a really big spike in initial enthusiasm, and that advocacy seems to be dying out a bit now. But I see no reason that you couldn't attempt to apply it. Yeah.
So I have 2 questions, because a lot of what you're saying rests on the conceptual understanding, the measurement of conceptual understanding. I know you haven't talked about that, but to me that's a really critical measure. And how you measure that can mean all the difference in the world. So particularly in this last case, you said there was no difference in conceptual understanding.
Right.
It really depends on how it's being measured.
Yeah, okay.
So I wonder if you could talk a little bit about that. I was also really surprised by your last answer, particularly because I was blown away because you said your provost went to somewhere, I can't remember where, saw this active learning and gave you guys this wonderful facility. And there is something unique about that certainly online environments can't capture. And so once again, it goes to how you're measuring. Is it really capturing what happens when you're face-to-face?
Yeah. Okay. So.
And MOOCs are not necessarily the good example.
No, of course. No, absolutely. For sure. But they certainly were the thing that people saw as the big transformation. So let me deal with the measurement of understanding first. You should be suspicious of conceptual understanding measures. For physics, we use the force concept inventory. For biology, we use the BCI. I know, there are problems.
So all that making these claims, this is where you make a claim that face-to-face, online versus what you're really trying to do at your university, in your physics program, are the same. It's like what you really trying to measure. There's probably other things happening.
For sure.
That doesn't get picked up on the force concept.
Absolutely, and I would never argue for using the force concept inventory as a singular measure, which is why we've tried to diversify and look at, triangulate with 4 sides. The conceptual understanding, attitudes, success. Because what we were seeing is differences in we saw a widening gender gap on the FCI in our physics classes. But we didn't see that as a measure of success when you look at passing the class. So for sure the FCI shouldn't be the only measure you're using. I know that well. But trying to think about what are all these different indicators where we would look at the classroom sort of from different angles. So what we saw is we saw no measured difference on these. So maybe I should say we didn't see differences in conceptual understanding. We saw no measured differences based on these instruments, which are relatively widely used. Yeah.
So I wonder also if it would be more powerful from your perspective, since you're dealing with modeling, if indeed you gave the students and the students in your section versus non-section actually measures modeling and see what they can really do. To me, it seems like that's a better measure of what you're trying to accomplish in the force concept.
Sure, I would agree with you. However, one of the things that we are very mindful of is that we have to talk to administrators who often don't understand that level of detail. And the force concept inventory, for all that it is wrong with it, it is a relatively robust, simple measure, right? In that the interpretation of it is not overly complicated, I think, especially for an administrator who is a political scientist or who might not know what these things are. They speak in bullet points, and so having these things, I think, is important. And I know that the subtlety of what is measured by an instrument that measures modeling, which I have a different difficulty with that, is that that's not useful in building up advocacy, right? Some of these things you have to do because that's the game that's being played. And I would like to say something different, but I don't. Yeah. Sure.
So isn't between what Joe is saying and what your responses are, it seems like the next logical step then might be to convince the people who are responsible for decision making that the ways of measuring transformation are inadequate.
Right, and we have been very careful to say we are always using multiple measures. So understanding attitudes, those are things that I can tell them and they don't need convincing that that's important. I mean, yeah.
So I'll try not to speak in bullet points. So one of the things that certainly speak to provosts and presidents is persistence in the evaluation. And we know, or at least we think we know, that communities and environments that people feel embedded in help them persist and succeed beyond introductory courses. Look, to me, like the data you presented was only sort of persistence from one course to the next.
Right.
Have you looked further downstream?
Yeah, these data have just, so remember I got there in about 2006, which is when the modeling classes. FIU is a large urban serving university, so we don't talk in terms of 4-year graduation rates ever. We only talk in 6. And often we talk about 10-year graduation rates, right? And so the time frame is just getting there. One of my postdocs, Ida Rodriguez, has just done this survival analysis. And what we found was pretty interesting, which is that after the modeling classes, we saw a drop in modern physics, particularly among women. Not a big drop, but that was the biggest drop. And then the students from the lecture classes, they sort of stair-step down the whole way. The students from the modeling classes, they dropped out at modern physics, but then stayed relatively horizontal, right? And so what this is saying is, and at the end there were no measured differences, right? And this is really important to our administrators. And so what this was saying is that, and our interpretation of it is, these students get to this modern physics class, it's a lecture class, and it doesn't engage them in the same ways. They haven't been filtered in the same ways as the lecture students have. And so they get there and they have this sort of like, oh hell, this isn't what I thought I signed up for. And they get out then.
So do you actually have?
Yeah, we have the data. I mean, honestly, like just 2 weeks ago, we've got it, and we're working on writing it up now.
Well, that's just persistence data. It's not actual interviews or.
It's not interviews. So the other study we're working on is looking at interviews and trying to get student stories. Yeah, to sort of more completely round out the picture. Yeah.
Can you show them, I think it was one of your last slides with the cognitive, Vygotskian, and ecosystem, yeah, this one. So my question is, why did you, somehow limit yourself and by thinking that what happens in the classroom can be observed only using cognitive lens? When getting out of the classroom, you use the Vygotskian lens. And then why did you need the? The ecosystem is a nice descriptive framework, but does it help you explain better the things?
I think that it does, because it makes me think. I mean.
Well, as a former ecologist, for example,
Yeah.
I had a problem to see the cultivating ecosystems because we are not supposed to cultivate.
No, of course not. Of course not. Yeah, well, okay, but you also sink ships to build artificial coral reefs. So this is not entirely, unheard of. And sinking a ship is sort of like transforming a physics department.
No, but being more serious, using Vygotskian lenses in the classroom. And the wonderful clip that you showed was a wonderful Vygotskian way to look at what happens in the classrooms.
Yes.
So why do you
because
yourself to the cognitive domain and using Vygotskian only to explain things that are beyond formal teaching?
So I think that what I don't have a good answer. That's a good question. I'm also not a cognitive person. I don't know what's in people's heads, so I don't have a good sense. But I think you could make pretty cognitive arguments about why you would get FCI results or why you would get CLAS shifts. You could really restrict your analysis to the analysis of people, right? Like individuals. And in order to get beyond that, in order to get to some of these questions of persistence, the theory that's behind persistence, you have to go beyond the individual, right? You have to go to the interaction and the engagement. And that's why, sort of, to me, it was sort of broadening outward. And maybe I shouldn't have, hierarchically laid them out. But I felt like the cognitive didn't adequately explain to me persistence. I mean, if it was just that the smarter kids stayed in the class more, that doesn't.
The other way around, that Vygotskian can explain everything.
Well, it's actually, I
don't know.
You
I don't
actually
know
have your units of analysis maybe are a little mixed up. So if you stick with an ecosystem allegory and make the Vygotskian sort of a community and an interspecific interaction,
Yeah.
And then the classroom focused is you're looking at one individual within a population.
Yeah, and yeah. I want to redo this slide. Any suggestions? Yeah.
Individual.
So Eric, this morning, or before this, I was talking to you a little bit more about some other research that you're doing that I would love for you to share with everyone else. Looking at what's happening in the classroom in terms of how ideas are shared and evolved over time. And I thought that's fascinating and maybe links to some people's concerns and interests.
Yeah, so I personally am very number oriented. I'm mostly quantitative. And some of these things you can't do real effectively quantitatively. And so I've been working with Vashti, who she's heard this anyway. She doesn't need to be here. But working with Vashti on a study where we sort of set up a theory about how models are constructed, and then tried to follow along with students in a small group. Actually, that clip is from our larger paper. Set up a clip where we say, okay, students are talking to each other. This is them sort of taking up this idea and learning how you might use it, and then bringing it to the larger class, and the larger class then kicking around, oh, these are the affordances and these are the constraints of that representation, and then eventually adopting it and utilizing it later on in the semester. And so that's a project that we've got. It's written up. It needs to be rewritten, but it's something that we're working towards. Because for sure, I think of myself primarily as Vygotskian, but I think that you would have a hard time getting to sustainability thinking only in Vygotskian terms. That's my sense.
Are there any other questions? No? Let's give it a final round of applause.
Thank you.